Monosaccharides are all well and good, but they do not make up all of the carbohydrates that exist in nature or that we use. Remember that we want to make our polysaccharides. Therefore, monomers or our monosaccharides need to be able to come together to form these bonds between these monomers. So taking it with small steps first, building a disaccharide. In each of our macromolecules, there is a unique bond or linkage that occurs between two monomers. In our saccharides, that linkage is called a glycosidic linkage. Glyco is a term we use for sugar. A glycosidic linkage forms when two hydroxyl groups from two monosaccharides react. We have seen this reaction before. An ether, which is an organic family that we have looked at, is formed when two alcohols react to put an oxygen between two R groups. That is what is forming here. So it is an ether bond between monosaccharide 1 and monosaccharide 2. In biochemistry terms, we call it a glycosidic linkage. Just like we have our alpha anomers and our beta anomers in the Haworth structure, we also can have alpha glycosidic linkages and beta glycosidic linkages. The direction of this bond is dictated by the first monosaccharide and the direction its hydroxyl group is going. So if you have an alpha monosaccharide, it's going to make an alpha glycosidic linkage. If you have a beta monosaccharide, it's going to make a beta linkage. And because this is going to be occurring between two monosaccharides, we also need to be provided the carbon number where these reactions take place. Monosaccharide 1 controls the direction of the glycosidic linkage. On this structure, our hydroxyl group on carbon number 1 is in the alpha position. Therefore, this is going to form our alpha glycosidic linkage. The hydrogen on monosaccharide 1 is removed with a hydroxyl group on the monosaccharide 2. Remember when we had talked about our ether formation, these are called condensation reactions because we are releasing water due to two separate molecules reacting. The organic chemistry term for this is an ether bond or an ether formation, and the biochemistry term is a glycosidic linkage. We know that this linkage is going to be in the alpha direction because of the alpha anomer of our first monosaccharide. So here is the glycosidic linkage that we are going to be forming. We know that this is going to be alpha. We also need to be aware of the carbon numbers participating in this linkage. So I'm going to go around and number each of my carbons. 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. What we can see is that carbon number 1, which is our anomeric carbon that is providing the glycosidic linkage, is reacting with carbon number 4. Therefore, this is an alpha 1,4 glycosidic linkage. Here we've got an aldohexose, so we have that 6-membered ring. I'm going to put that oxygen in that kind of top, that 1 o'clock position, or that top right-hand corner. So here's my anomeric carbon. On my anomeric carbon, that hydroxyl group is going below the carbon plane. So this is our alpha anomer, which means it's going to make an alpha linkage. On my second monosaccharide, again, putting that oxygen that's in the ring at that 1 o'clock position, or the upper right-hand corner. It is going to be reacting with carbon number 4. Notice that carbon number 4 is also going down. That allows for the proper orientation for these two hydroxyl groups to interact. I'm going to pull the hydroxyl group off monosaccharide 2, the hydrogen off of monosaccharide 1, so that then I can bond these two monosaccharides together. Orienting, I have my cyclic, my oxygen and my rings at the same position. So here is my alpha glycosidic linkage between carbon 1 and carbon 4. And you can see that the bond is going below the carbon plane. So as we have seen, it is going to be the hydroxyl group that is on carbon 1, or the anomeric carbon of our first monosaccharide, that is going to dictate the direction of that bond. Since this hydroxyl group is going above that anomeric carbon, that is our beta anomer. Because it's going to be a beta anomer, it's going to make a beta bond, or glycosidic linkage. The hydrogen of the anomeric hydroxyl group is going to react with the hydroxyl group on the second monosaccharide. This is going to then remove water, the condensation reaction, forming that bond between the two monosaccharides. Looking at that anomeric carbon on the first monosaccharide, it produced that beta linkage because it's in the same direction in which it started. We need to know the carbon numbers. So here we have carbon 1, here we have carbon 4. Thus, this is a beta 1,4 glycosidic linkage. Looking at our first monosaccharide, putting it in proper orientation with that oxygen that's in the cyclic in the upper right-hand corner, or the 1 o'clock position. Carbon 1 is that anomeric carbon, and we can see that the hydroxyl group is going above that carbon ring. So this is a beta anomer. This means it's going to make a beta glycosidic linkage. I'm going to have this react with carbon number 4 of monosaccharide 2. I'm going to remove that hydroxyl group from carbon number 4 and the hydrogen from our reactive anomeric carbon. And then that's going to allow me to form that bond, or glycosidic linkage. So now we have monosaccharide 1, monosaccharide 2. Here with monosaccharide 1, you can see that the bond, the beta, is going up. So this is a beta 1,4 glycosidic linkage. And it kind of creates, let's see if I can do this with one hand. It creates like a step. So you have to go up and over with each of those beta linkages. Here we have 2 ketohexose monomers. We know this because they are 5-membered rings. Remember on our ketohexose that it is carbon 2 that is that anomeric carbon that we are going to be looking at for classifying the anomer present. Based off this structure, the hydroxyl group is going below the anomeric carbon. Therefore, this is our alpha anomer. And our alpha anomer is going to form an alpha bond. We are going to take the hydrogen off of that reactive anomer and the hydroxyl group off of this carbon number 6. Note that this is the first time we've seen that we can react with carbon number 6. Keep in mind, we could react with any of the carbons that have a hydroxyl group. So you really need to pay attention to the numbering of our carbons. Carbon 1 is up and out of the ring. Carbon 2 is that anomer carbon. Then we have 3, 4, 5, 6. Do the same thing on our other monosaccharide. We have 1, 2, 3, 4, 5, and 6. Reacting between carbon 1 and 6, we get that alpha glycosidic linkage from monosaccharide number 1, and it bonded to carbon 6. Therefore, this is going to be an alpha 2, because our anomer carbon is carbon number 2, and it bonded to carbon number 6. This is an alpha 2,6 glycosidic linkage. All right, so here we have our two fructose molecules, and we are going to be reacting. So here's carbon 2, our anomeric carbon. The hydroxyl group is going below that carbon ring. So that means that this hydroxyl group is going to be reacting with carbon number 6 on the other fructose molecule. So here's carbon number 6. It's going to react with that hydroxyl group. So I'm going to take that hydroxyl group off of carbon number 6. The hydrogen off of the anomeric hydroxyl group. We're going to form water. So now that OH group that is on the anomeric carbon can bond to carbon 6 of the second monosaccharide, creating an alpha glycosidic linkage. And you can see that in this linkage that the molecules are stacked. What's important is to notice that I have the oxygens that are in the ring up together so that they're oriented correctly.